In a microservice architecture, you usually split your system up into multiple services that could be represented as multiple boxes. Now, in your system, you need these components to communicate with each other. And there are multiple ways you can do this in a microservice architecture. I want to take you through an example to showcase some of the way you can do it, some of the problems you can encounter, and how we can solve these problems. So in front of me here, I have a diagram showing a basic e-commerce site. On the left, we have a order server, which is responsible for managing the orders of the user, like what they have placed, the status of the orders, etc. On the right, we have an inventory service, which is responsible for managing what you have in your inventory, what items you're selling, and how many you have of each items, and details like the price and all that stuff. Now, when a user creates an order, you need to communicate with the inventory service so that the items the user has in their order is reserved. Now, the first solution to this, the simplest way is just to send a simple HTTP request from the order service to the inventory service with all the details needed so that the inventory service can handle and reserve all the items so no other users can purchase the items. You can update your quantity so your website shows the correct amount after the user has placed their order. Now, there could be some problems with this. One of the problems is that what happens if there is some sort of network error or your inventory service is down? Something unexpected happens so that the request you send from the order service never reaches your inventory service. Now, there are things you can solve this. You can implement some sort of retry mechanism in your order service. Now, the problem with this is that your order service should be as isolated and focus on a single job, which is managing the orders. You don't really want to bloat this with a lot of different things like retry mechanism. So this is one of the problems with this first solution. Another thing is, what if we have multiple services? For example, we have a cart service, which is responsible for tracking what items the users have in the cart. Now, when they place an order, we typically want to empty this cart. So now we need to update our order service to also send a request to our cart service so that they can be cleared and emptied. Then we also have an email service. Whenever a user places an order, we do want to send them a confirmation email. So now again, we have to go into order service, we have to update the logic so that it sends a request to the email service. As you can see from this example, this is a solution that doesn't really scale all that well. We have tight coupling between the services. The order service needs to know about all the different downstream services that needs to know about the order being placed. When we add a new service, we have to modify the producer, which is going to be the order service in this case, to actually send the request to all the different services. There is a single point of failure if something unexpected happens on the network. Now, as I said, we could implement some retry mechanism for this, but this is not really the job of the order service. And this is something that is hard to scale independently. So how do we solve this? Well, the solution is something called an event broker. There are different tools out there that you can simply start using out of the box. And these are things like Kafka or RabbitMQ. And what we do with this is we place them in between. So now the diagram look almost the same, except we have the event broker in the middle. Now, when we start the order service, we connect it to this event broker. And whenever a user places an order, we simply publishes an event to the event broker. Similarly, all the services on the right, the inventory service, the car service, and the email service, whenever they start, they connect to the same event broker and they subscribe to this event. And then it's the job to the event broker whenever it receives an event from a producer, which is the order service in this example, it will forward the event to all the different consumers that have subscribed to that event, which is going to be the inventory service, car service, and email service in this example. And this scales much better. The producer doesn't need to know anything about the consumers. They can connect and subscribe to the events as they like and also unsubscribe. When we add a new service, we simply just subscribe it to the event. We don't have to modify any of the code in the order service. This is much more loose coupling. And usually the services like Kafka or RabbitMQ has implementation for like retime mechanisms and fault tolerance. And this is much easier to independently scale. Okay, so this looks really nice in a diagram, but how do we do this in code? So let's jump over to our editor where I've implemented the exact same example so we can see how we can do this in practice. Okay, so now that we're in our editor, let's see how we can implement this in code. So I have a project here where I have two apps. I have one inventory API and I have one orders API. I also created a Docker Compose, which you can see in our editor, which is just a RabbitMQ container that will spin up a local container I can use for this example. I will leave a link to this example in the description, so if you want to take a more deep dive, you can always visit the code there. So if we go over to terminal, I'm just going to start the local RabbitMQ service or container so that we actually have something to connect to. Then we can take a look at our order service. This is a HONO API, and it is really basic for this example only. The first thing we do is that we grab the broker URL from our environment variable. This is something I set in my env. Since I'm just running it locally, I'm just connecting it with a username and password guest and the IP of localhost. Then I create the HONO application or the HONO API. Then I create the broker client, and this is something I create from this message broker class. This message broker is a class I have created that wraps the RabbitMQ client, and if you jump into it, we can see how it is implemented. It is a class with a constructor where we pass in the URL. This is the URL to the broker we want to connect to. Then it has three methods. It has this connect method, which simply connects to the broker. Then we have a publish method, which takes in the queue name and also the message that we want to publish. So what queue we want to publish to and what message or event we do want to publish to that queue. Then we have a subscribe function, which also takes in a queue, so whatever queue you want to subscribe to. And then we also need to pass in a handler. This is going to be a function that will be executed whenever a event or a message is received from this queue. If you want to take a more look at how this is implemented in the code, you can just pause the video for now. Or, as I said, there's going to be a link in the description. So if we go back to the application, now that we have our broker, we can connect to it. Then we create our orders API. This is the API the client is going to send a request to actually place the order. The first thing we do is we get the user ID. As this is a basic example, I'm just hardcoding it to user one. But this is something you will typically get from your auth token or some sort of session. Then we grab the body, which is going to contain the items that the user actually want to purchase. Right here, I'm just simply getting it from a request. You typically want to do some type of validation, but I just skipped it for this example. Then we want to do some sort of processing for this order. For this example, again, I'm just doing some simple logging. I'm not doing anything. But then when everything is done and everything succeeded, we can now finally publish the event. So I'm now calling this broker client again that I created above. We're calling the publish method, and then we're passing in the queue. So in this case, it's going to be an orders event, signaling that this is events from the order service. And then we pass in an object, which is going to be the message that we want to send to this queue. We're giving it the type in this case, which is order placed. This is because our order service can essentially publish multiple different events. In this case, we only have one, but you can think of it like we have one for order placed, maybe order canceled, or things like that. Then finally, we're passing in data into this event, and that is all the useful data that is relevant to this event. So that's going to be the user ID, who actually placed this order, and the items, so what items was actually part of this order. And then we're just doing some more logging before we return a successful state. That is all we have for the order service. If we take a look at the inventory service, you will see that it looks really similar. We get the broker URL from the environment variable, and we create our HONO application. Then we create our broker client, which again uses the same class. And then we connect to it. The difference here is that for this example, I haven't implemented any endpoints. What I'm doing is I'm simply subscribing. So on this broker client, we have the subscribe method that I'm calling. We're passing in the order events. So this is the same queue that the order service is going to publish to. And then we also pass in a handler function. This is going to handle or be executed whenever we receive an event. As you can see, this gets the event. We extract the type from the event, and then we switch over the event because, as I said, the order service can publish multiple different events. In this example, as it is basic, we only have one event, but you want to handle them differently. So we switch over the type, and then if it's order placed, we call the handle order place function. And here you can then do whatever you should do, like reserving the items and all that stuff. But for this example, again, I'm just doing some logging. So if we now go over to our terminal, I'm first going to run the order service. Then I'm going to create a new terminal where I'm going to run the inventory service. I also prepared a Bruno request that we can send to our order service. This is a request that we just sent to the order API that we created. We give it the body, which is going to be a list of items, and the items is going to include the ID of the item and the quantity, so how many of that item we want to purchase. When we send the request, we see we get 200 OK and a successful state. And if we go over to our terminal, we can now see on the left, we have the order service. We received the order request. It had the data user with user ID what. This was the hard-coded thing, but yeah, this is something you get from the token. And then we see that it had items with the ID, item ID 1 and item ID 2. Then we process this, like simulating processing. Then we publish the event to orders.event. And then we can see that the event was published successfully. In our inventory service, we can see that we received the event for order placed. It had the data user 1 and item ID 1, item ID 2. And then we successfully processed the reservation and then inventory reserved successfully. Of course, this is just simulation, but you get the idea. So this is how you want to include event-based communication in your microservice architecture. Now, before I end the video, I just want to say one more thing, and that is it's not always the case that event-based communication is the perfect fit. It's not a one-size-fits-all. And we can see that in this example, we are sending from the client an array of items, but the items only include the IDs and the quantity. We don't send anything like the price or the name or anything like that. And this is with intention. If we sent that message from the client, we couldn't really trust it on the server anyways, because then the client can just modify the price. So what we have to do in our order service as part of the order processing, we actually do need to send a request to our inventory system to check, do we have these items, or are the IDs of the items that the client sent actually valid? Do we actually have these items? Do we have enough in stock? And also get the details, such as the name of the item and the price, so that we can calculate the total price of the order. Now, for this type of communication, it's actually better to just send a simple request. But when the process is done and we have successfully created the order, then it makes more sense to publish an event and use event-based communication. So this just shows that sometimes event-based communication is what you should aim for, but other times it makes sense to just keep to the basic and use simple requests. With this, I hope this video helped you understand how you can do different types of communication in your services when you have a microservice architecture. If you have any feedback, please leave a comment. And if you like the video, please give it a thumbs up. And then I'll see you in the next one.